Hi, everyone. Welcome back from the coffee break. Hopefully you were able to get some snacks and some caffeine if you consume it. My name is Madison again. I'm the session chair for this morning. And I have the great pleasure of introducing Chantelle Chan and Tanzim Mokammel for their talk about graceful deletes. Please, take it away.
Thank you.
Ooh. Oh, wait, is this? Okay, perfect. Give me just a second to set this up. Okie dokie, awesome. Thank you all for coming today. Today, Tanzim and I will be giving a talk about a project we did at Cohere, all about queues, asynchronous tasks, and distributed state management, and how we use that to enable user deletion across application and network boundaries. Tanzim, do you want to introduce yourself?
Hi, everyone. Thanks so much for coming. My name is Tanzim. I've been at Cohere for 2 years now, and prior to that, I have full stack development experience across e-commerce, fintech, and in a past life, I worked on semiconductors. Most recently, I'm working on the North project, where I focus on everything related to retrieval augmented generation, as well as third-party API integrations. And outside of work, I enjoy traveling, photography, and video games. So if you're interested in any of these things, feel free to come catch up with me after.
Awesome. I am Chantelle. I've been at Cohere for 1.5 years now. I work with Tanzim on the North Tools team. So that means all my work revolves around rag file tools and tool performance and evals. So if anybody wants to chat about any of those things after, hit me up. Or you can talk to me about cozy video games, because I do a lot of that as well. Okay, so today we're going to talk about a system we built at Cohere using queues to dispatch asynchronous tasks for data removal across application and network boundaries. I'll go over the initial problem and the high-level architecture, and then I'll talk a little bit about the different queue systems that we considered using for this project. Afterwards, Tanzim will take us through the actual implementation, adjustments we made along the way as a result of unexpected technical challenges, and then finally, we'll wrap up with where our project is going next. So to briefly set the stage and give some context around the problem we're solving, let's go over the context of the system we're working inside of. So Tanzim and I work on North, which is Cohere's agent platform. We use Cohere's command models for generation, and we use our in-house parser and vector database service for searching. The command models are optimized for tool use, reg, and citation generation. We handle content ingestion and parsing using our embed model, and then we use re-rank model for semantic search across indexes in our vector database. Our team focuses on connectors, both internal custom tools and MCP tools. That means that we're building out the tool integrations that give North the ability to interact with third-party sources to either gather information or perform actions. So here's the problem. As users come and go in a given deployment of North, how do we guarantee that their data is cleaned up asynchronously in a predictable and fault-tolerant way? We've got multiple data stores to clean up here across application boundaries, and user data is scattered across our core North database, the sync service DB, the rag service vector DB, blob storage, our auth service DB, as well as our RBAC service database. Making this even more tricky is that separate teams own each of these sources of user data, and we also have to consider the fact that user delete can't be allowed to block normal operation of the application. Additional considerations here are race conditions in deletes between each of these services, how the different services depend on each other for consistency across databases, unintentional table locks here due to cascading deletes that can get really big, and recovery from failure for each step of deletion. So the core user story here is that an admin, somebody leaves a North deployment, and then the admin goes in and is like, hey, an admin panel, I want to mark this user for deletion. That user should be immediately locked out, meaning that their RBAC and auth information should be removed. However, the admin shouldn't have to wait for deletion of all other user information for them to take another action or proceed to do something else. We just want to make sure that eventually private agents and files do get permanently deleted. Okay, so there's a few additional considerations here that were outside the scope of our first milestone, but we do need to consider them in the overall design of the system to make sure that what we build now is extensible to these options in the future. So since we plan to cover soft or recoverable deletion, retries, and ownership transfer of agents, files, and automations, we need to be aware of the extra state tracking that we'll need in the future to enable these features. Especially for file transfer, this is going to be pretty tricky because we have to consider 3 separate systems here that interact. So that's the Core North database for the file record, the raw bytes in blob storage, as well as the vector representation of the file contents and parsed file contents in our vector DB. So there's quite a few ways for us to go about implementing a messaging system and async task workers in Python to accomplish this goal. However, it is important for us to note here that North is on-prem first. So that means we can't reach for like a default solution of AWS SQS or the GCP Cloud Tasks, for example. We looked at a few options here, but we spent most of our time debating between using either Celery or Ingest. So Celery is by far and large the most popular Python task queue library, and it has a super active community with a lot of available support. And its popularity and maturity is like one of the reasons that it's quite widely used at Cohere. But that's not to say that we haven't run into issues with it in the past that we found tricky. Particularly, we've seen issues on our team around garbage collection, memory leaks, and broker disconnection issues with Redis. So due to that, we had room in this project to consider other solutions. Ingest is definitely more newly adopted at Cohere, but we've seen it perform quite well for other teams and systems that need async tasks and queues. It offers a higher level of abstraction than Celery, so it's more focused on this concept of like durable task execution triggered by events. We're particularly interested in Ingest just because it gets us a lot of desired features out of the box that we know we're going to want down the line. So that's stuff like locks, prioritization, partial function retries. We also considered a few secondary options, such as procrastinate, Nats, and using just a Kubernetes cron, but we ruled all 3 of those out pretty quickly. So procrastinate works quite similarly to Celery, but it's using Postgres as the messaging broker instead of Redis or RabbitMQ. It offers some of the nice additional features that we did want, such as prioritization and locks. But ultimately, we decided against using procrastinate just because the project is a bit smaller with fewer active maintainers, and we were worried about ability for us to get support. Nats is used as a messaging service backing queues in other projects at Cohere, and that's worked out quite well for them, so we investigated how we'd go about implementing this in Python. But if we chose Nats, that would require us to implement task persistence, cron scheduling, and worker management all from scratch. So due to that being quite a lot of scope creep on an already large project, we ruled out Nats. And finally, we looked at the initial sanity check thought of hey, what if this was just a Kubernetes cron and we had it spin up a backend pod just to run our deletion service. While that's really great for testing out our service in prototyping, in production, we want the ability to scale task workers independently. We want prioritization, subtask retrying, ideally memoization, and we also want rate limiting. So in order to not build all of those components out ourselves, we had to rule out the Kubernetes cron. So for all of those reasons, we chose Ingest as our async task worker for this project. As mentioned, the core of this system is the async task queue. So on a scheduled cron, it's responsible for dispatching our initial task to find users who are marked for deletion in our database. Auth information stored in the RBAC and auth service databases were immediately removed already to lock users out of the system and prevent them from accessing any agents or files that they previously had access to. Then, for each user, we go and we check whether or not a per-user cleanup task has already been queued. So if it has been, that's great, it's a no-op. If it hasn't been, we go and we gather the associated resources for the user. So that's all of their conversations, their agents, their files, any automations that they may have set up in the past. And then we go and we dispatch one task per user per service back into the same queue. The same worker or our set of workers then goes and it picks up those tasks off the queue, and then it runs each of those subtasks to execute the cleanup. So recall from earlier that I mentioned that file content is kind of tricky because we've got our core north database, our vector database, and our blob storage to consider for this. That's because we have some tools that we use that require the raw bytes from blob storage, but other tools need the parsed text content, or to perform semantic search, it needs the vector representation. So in order to clean up the file entirely, we have to launch 2 separate tasks for cleanup in each storage location. Before we can actually start the VectorDB cleanup process, we have to make sure that any potential current document syncing gets canceled. So we could do this by launching cancellations, waiting for all of those to succeed, and then coming back and doing our cleanup. However, that takes quite a while, and it's a lot faster for us to just overwrite the access token for the user, which will cause all other requests to eventually fail. We can remove the user's identity after that from the VectorDB user management service, and then that'll let us remove all documents to all agent IDs and user IDs associated to that user in our VectorDB index. From there, there's a separate asynchronous task within the VectorDB management service that periodically cleans up any documents that no longer have any parties with access. So we've already stopped the sync service from adding any new files by overwriting the access token in the last step, but we do still want to purge any remaining user data from the sync service itself. So that includes any RBAC information or connection information to third-party services that are used as sync sources. After each cleanup subtask finishes, we need to perform a check to see if all of the cleanup subtasks for a given user have been completed for the sync service, document service, and document raw bytes service. And if everything is completed successfully, we are finally okay to queue our final deletion task. That takes care of removing all of the user's information from tables in the core north database through a series of managed cascading deletes. Finally, we are able to mark the entire user delete task as successful. So after taking this through a few iterations and working through the pieces with all of the teams involved, we arrived at an initial high-level design. The main parts we need to consider here are the async task queue system, which takes care of launching our initial discovery cron, the initial task that then finds users who need deleting and is responsible for launching subtasks necessary to remove the data from each subsystem. Some of these subtasks are allowed to be executed in parallel, but the final removal requires that all prior tasks have finished before it begins its execution. So each subtask needs to report its status back out to a central store. At this point in the project, I needed to step away to handle a high-priority customer ask, so Tanzim drove the software architecture and implementation from here.
Yeah, thank you so much, Chantelle. So one of the first things I wanted to do after all of the planning and alignment was driven between the teams was take the overall business requirement and simplify it down to a few essential aspects. And that is what this diagram represents here. So essentially, there are 2 splits where we have one set of actions that happen immediately, and then there's another set of actions that happen eventually. And this is going to be a core recurring theme for the implementation. And in this diagram, we can see that the thing that we need to perform immediately is to mark the user soft-deleted and then revoke all of their tokens so they're no longer able to use the platform. And this is a very quick action, and this allows the admin to perform the action and appear as if everything had been completed and get control back and continue anything else they were doing. But in the background, there was a lot of work that's still remaining, and those elements are what some of the items Chantelle already mentioned, and that is to fire an event per user and then clean up all of the data sources. And in our case, that was the vector database, and then as well as the blob storage, which is tied to our MyFiles feature. And finally, the database rows within our core database to clean up the agents, conversations, as well as any other user-related tables. So moving on from this simplification of the process, I wanted to explode back out and plan the overall set of execution and break the implementation into a set of pull requests, as well as how we can incrementally deliver an end-to-end test. And this is also reflective of the slide just prior to this, and it breaks down the problem into a set of immediate actions and eventual actions, and then further breaks it down into the different data sources that we would need to clean up, and how we can deliver that incrementally and be able to make sure that everything is functioning. And this was particularly helpful in setting up some of the infrastructure. We were one of the first teams to implement this solution or use ingest as a task orchestrator. And one of the things we were able to do was set up a set of mock logs that would fire off cron tasks and then pretend as if those actions were being completed by simply logging to make sure that everything within the overall Kubernetes cluster was working as expected. So from here, we move on to some of the principles within the software design itself. And a core implementation principle for us was the dependency inversion principle. And we were able to achieve this through the concept of interfaces and dependency injection. And this ultimately allowed us to build modular, easy to maintain code despite the volatile nature of some of the underlying details. So looking at the interface, this is a very common principle in Golang that we brought into Python. And essentially what this allows you to do is implement duck typing. So you can see in our example here, we have the user Graceful cleanup protocol, which defines a set of function signatures, including their arguments as well as their return values. And then from that point forward, we implement a concrete instance of this interface and then pass that as a dependency into the overall user delete service. And there is a bit of a contrast to perhaps a slightly more popular approach to similar problem solving, which would be the abstract base class. But in this particular scenario, we much preferred the protocol because it somewhat got rid of, or it encourages composition over inheritance, and that was very useful in meeting the requirements that we wanted to have within the overall software architecture, which once again were maintainability, extensibility, as well as testability. So looking into detail into some of the interfaces, well, this is the interface itself. As you can see, this is the syntax for it in Python. You essentially develop a set of arguments, their types, as well as their return values, and then we can see how it gets used within the delete user service and how it allows you to hide a lot of the complexity of the underlying layers, such as API calls to the vector storage solution, database queries, and mutations. And you can see the dependency injection here as well, where in the constructor, we pass in an implementation of the interface, which also helps us in test because you can essentially create any mock test services that match the interface and be able to assert against the behavior of the service without necessarily worrying about, let's say, which database drivers you're dealing with. Moving on to the most client level usage of this, which would be at the router layer. So this is what the router for the mark user deleted looks like, which is the initiation of the soft deletion process. And you can see that it looks extremely simple. And this is because a lot of the complexity is hidden away under the layers of abstraction. And this is looking at the immediate action that we perform. But with the next slide, we can see how this gets leveraged across the eventual layer as well. So in our case here, we have a cron job. A bit of a technical difficulty here. Can I just click on this? No. Okay, yeah, there we go. So yeah, we can see that we have a cron job that gets fired every 5 minutes, and it picks up every user that has been marked for deletion. And for each of these users, it fires tasks, and those map back to the different cleanup activities that we mentioned earlier on in the slides. And then at each of these tasks, we leverage the underlying interface that we had dependency injected into our overall service. And one thing to note here, which segues us into the next set of slides, are the opportunities for concurrency, and we had 2 layers of concurrency as well. There's one layer that allows us to optimize the individual tasks, but at the same time, we need to ensure that we don't have race conditions or deadlocks and idempotency at the overall system layer. So I'm going to get started with what I'm calling the micro concurrency here, which is the concurrency layer at the task level. So what we wanted to do was to have the tasks run as quickly as possible. And in order to parallelize certain things, we looked at the state dependency between the individual tasks, and that gave us guidance in terms of what we can run concurrently versus what we can run, what we need to run serially. And in our case, there were no dependencies between the vector store cleanup and the blob store cleanup. However, there were certain things that needed to finish before we could delete all of the rows in the database. So those got mapped to the sequential events that would happen after the parallel cleanup was done. And one of the things I wanted to also highlight was the syntax for using the ingest APIs. You can see that it looks very similar to, let's say, concurrent JavaScript or async IO Python. However, there's a lot of stuff that's happening under the hood that allows us to do durable function execution, which comes out of the box for ingest. So moving on to a higher level concurrency pattern that we needed to employ, and that was being able to use optimistic locks to make sure that there weren't multiple instances of workers that were doing the exact same thing. And the way that we were able to achieve this was to create a table within the database that allows us to record when a certain task with the composite key of the user ID, as well as the task ID, were started at. And then we also recorded any steps when certain things were completed, and then any errors that came along the way. And what this allowed us to do was answer a few key questions, such as, hey, did the task of vector store cleanup run? Why did the user's delete fail? Is a certain task still running? Did it crash? And can I safely retry some of the tasks? And there is out-of-the-box support for this within ingest. However, there are limitations. For example, your composite key is only durable for 24 hours, which didn't necessarily meet our initial implementation requirements for the project. And because of this reason, we implemented this by hand using the Postgres database, as well as a set of decorators within the tasks code that I demonstrated earlier. So with that, we wrapped up our MVP for the Graceful delete item. However, as you may have noticed throughout the presentation, there are certain things that were initially considered but were not quite completed, and there are lots of improvements that can still be made to this implementation. And I'm going to pass it back to Chantelle to wrap up the presentation with those considerations.
Thank you, thank you. Okay, so in the first version of this project, we didn't get the chance to address ownership transfer, grace periods, and soft deletion, and having a full-fledged admin dash for surfacing deletion errors and retries. Luckily, an adjacent North team is picking up the ownership transfer aspect of this project, so we're really excited to see where they go next. All right, thank you all so much for your time and attention. Does anyone have any questions? Yes. So why did you pick ingest again? We really liked all of the features that we got out of the box with ingest that would allow us to do stuff like memoization of sub-function results, not so that we wouldn't have to like repeat units of work across future retries. And we know we want that eventually with like the full-fledged admin dashboard with stuff like ownership transfer, where we expect there to be a lot of tricky additional states to manage. Do we have time for one more or? Oh, okay, so sorry. Okay, ask me questions.